This video will run through the process of factoring, removing a GCF factor, and then analyzing the pattern. So for this particular problem set, you're going to either have a difference of squares or a perfect square trinomial left over after you factor out a GCF. So it will give you practice removing a GCF and then factoring the polynomial that remains one more layer. So a problem like number 1. Numerically, they share 3. So if I factor out a 3, I'm left with this. And then you recognize that that is a difference of squares pattern. So then you would need to go one more layer. So in order to be completely factored, you would need to break the polynomial down into as many small pieces as possible. Okay, let's look at a problem like number 2. 5 is the GCF among all of the coefficients. And if I factor out a 5, then what remains in this particular problem would be the perfect square trinomial. 9 is a perfect square, its square root is 3, and 3 plus 3 is 6. So I would then further go one more step, and I would break this down. You can present it like this, or you would have the option to write the binomial factor of x plus 3 twice. Either presentation is correct. Okay, let's move down and look at a few from the next problem set. Starting with number 1. They're both going to share the factor, the numerical factor of 2, and the highest power of k found in each is k to the first. So if I factor out 2k, what remains is k squared minus 4, and then I go one more layer, break this down to k plus 2, k minus 2. And then let's do a few more. You probably are starting to get the idea now. These are nice problems for learning how to factor, for understanding the process. Let's look at something like number 7. Numerically, the coefficients all share a factor of 5. And then it looks like the highest power of k is going to be k to the first. So if I factor out 5k, I'm left with k squared plus 20k plus 100, which is your perfect square trinomial. The square root of 100 is 10. 10 plus 10 is 20. So this is going to factor completely. And then you would have the option of writing k plus 10 twice, beside itself. Both presentations are correct. Okay, let's move on and do a few more at the bottom so that you get the idea and just get comfortable with the process. Let's do one down in the last problem set. And it just starts to get more cluttered. And let's see, let's do a problem like number 10. So in number 10, it looks like common to all three terms numerically, it's really just going to be the factor of 2. And then analyzing the variables, they really don't have, the only variable that they all share is b raised to the power of 2, b squared, b squared, b squared. So if I remove or factor out 2b squared, then what's going to remain behind is going to be 16a squared and 8a. And then from the last term, well, this is actually a really good example. When I remove one of the terms completely, what remains behind is a positive 1. Because I need to have something to multiply the factor that I removed by. I would need something to multiply that by if I had to create the polynomial right back. So in the world of multiplication, when I factor the entire term out, what remains behind is a 1, not a 0. And now I would simply break this down. This is a perfect square trinomial. And this is going to break down as the square root of 16a squared is 4a. The square root of 1 is 1. I'm adding the term in the middle, so that means that my monomial or my binomial factor is going to be addition. I would put parentheses around that and square it. And then I need to make some more room on the board. And then I would simply copy the factor that I removed or factored out. And this would be the completely factored form of that particular problem.